Hi, this is Physics 1, Chapter 15, Part 2. We left off with abiotic processes. And as I said before, go through kind of a little recap. When we hold pressure constant, we have what's called an isobaric process. When we hold temperature constant, we have an isothermal process. And when we hold volume constant, we have an isovolumetric process. And so with these, the isovolumetric, you have the pressure change, but you don't have a volume change. And with the isobarometric, you have a pressure change, you don't have the pressure change, but you have the volume change. And then isothermal, you have both the pressure and the volume change, and you don't have the temperature change. With abiotic, you'll have both pressure, volume, and you will have a temperature change. Right, and so it's a little different than isothermal, but it does have a curve to it on the pressure volume graph. Right, so for abiotic process, the big thing is no heat is being added. Okay, so up to this point, we always had Q being a part of it. In this process, Q equals 0. Right, so you don't add heat. If heat is added, or I should say if energy is added, it must all go to being done by this, or work done by the system. Right? And so compressing or expanding a gas happens, and no heat enters or leaves the system. Okay, so in this example, we have a cloud of gas, of any kind of gas, I guess, or just air in itself. And when it's lower, it's at 15 degrees compared to the ground, which is at 25 degrees Celsius. As it increases, the temperature goes down. And so this parcel of air, this air pocket, kind of will start to expand and increases to -5, and, well, I should say decreases to -5 and expands even more in volume. And decreases to -15 and expands even more in volume. And so no heat is being added or taken away from this as this air parcel increases in height and increases, or drops in temperature and increases in volume. One way they can achieve this is through insulating a system of gas. All right, so the way the equation will look is we have delta U equals Q minus W, and Q is 0, so delta U ends up equaling just a negative W. So the negatives there for when you have an increase in energy due to work done on the system, you have a decrease in volume. And a decrease in energy due to work done by the system, you have an increase in volume. Right? So when your work is done by the system and this ends up being a negative W, negative energy change, you end up with an increase in your volume. And when the work is done by or on the system, you end up with a negative energy change. I'm sorry, that would be negative. So you end up with a positive energy change, and work is done in decreasing the volume. So let's get to this example here. Now, one thing I want to point out that I haven't mentioned yet, but we've seen this in other chapters. Delta U equals 3/2 nR delta T. Okay, we saw this in, I think, starting in chapter 13 and then 14 and even this chapter, so it kind of makes it way involved in different parts. But N is number of moles for gas, R is a gas constant, so R is 8.314. So when we have 8.5 moles of an ideal gas expanding abiyotically, performing 8,300 joules of work in the process, so the work is 8,300 joules. What is the change in temperature of the gas during this expansion? So we have 3/2 nR delta T has to equal a negative work. Alright, so we know what work is, we know what the R constant is, we know what the moles is. We need to find out what this temperature change is. So we're going to multiply, or actually multiply over by 2/3, so you end up with delta T equals 2/3 nR and then a negative W. And so delta T would equal 2 times 8,300 over 3 times 8.5 over 8.314. My calculator and try and find where it went to. Right, so 2 times 8,300 divided by 3 divided by 8.5 divided by 8.314. And you get 78.3 Kelvin, which is going to be negative because of that negative sign. 78.3 Kelvin. Right, so there's a decrease in temperature, and we didn't get the original temperature, so we don't really know exactly what the temperatures are, but there's a decrease in temperature of 78.3 Kelvin when this increases in volume, and has 8,300 joules of work done in the process. Alright, so now the second law of thermodynamics. And so we talked about the fact that the energy has to be conserved, and that was the first law. The second law deals with the flow of energy. And so there's going to be two ways we tend to look at the second law. Okay, so second law of thermodynamics. This is based on the direction that energy tends to flow. This tends to is actually kind of important here. All right. Heat itself never spontaneously flows from a cold object to a hot object. Right. Heat can only do this, flow from a cold object to a hot object, if one of two things happen. Work is done on the system, or by adding energy from another source. Okay. Another way we look at this is order tends to disorder. Right? So, as we see in this picture, normally we don't look at something like a broken glass being put onto a shelf and being put onto the shelf where it's perfectly intact. That usually doesn't happen. Most of the time, it goes the opposite. Glass is on the shelf, gets knocked off by a kid, and breaks. If you have kids, this always happens. We have a cup on that we put on the fridge, and over time the kids will use that cup, and it has pens in it. And when they put it back in the fridge, they always put it right there on the door, on the top of the door. So you open up the freezer and it falls every time. Once they get done, they never know how to push it back. So this is for them to for it to be opposite, and they put all the pens back and put it on top of the fridge correctly. It just never happens. All right, so in terms of energy, we look at this as quality goes to waste. You start with quality energy, you end up with wasted energy. Right? Example, we have a car. Right? Put a little pipe on here. Gas tank. I'll actually draw in a gas tank, and I'm going to color this. Put gas in the gas tank. Right? Quality, energy. Right? This is, in a sense, you can call it potential energy. It's energy that can be used to get this car going. Car starts to go, and you have your exhaust. This is wasted energy. The exhaust is energy that's not being used to move this car. Right? Some of this gas is used to move this car, others is not. This is why, if you think about it, why certain cars have better fuel mileage than others. If that didn't happen, if the amount of gas you put into a car always got used to move that car, then the cars would pretty much have the same miles per gallon. And even if they didn't, because some have bigger engines maybe and a bigger mass, the smaller cars were roughly the same size will always have pretty much the same miles per gallon. But we know that if you drive a car, if you drive a certain way, you can actually save on your miles per gallon. So if you don't drive too fast, that helps keep the miles per gallon down. If you fill up your tank at half a tank, it's known to keep the miles per gallon higher instead of losing your miles per gallon. So highway driving a lot of times also allows you to get a steady miles per gallon going. That's higher than if you were doing a lot of stop and go traffic. And so there is definitely wasted energy, wasted fuel when we're driving a car. But when you put in the gas, you're putting in quality energy. All right, so this is also an example of heat energy going from, well, I won't get into that just yet, but this is the difference between wasted and quality energy. So if we looked at, I have in here molecules, but I'm going to do it with people. Let's say you have basic training. The people come into basic training and they all just gather around. I probably shouldn't draw that many people, but they all just gather around. And there's no rhyme or reason to why they're standing. They're just milling around. Doesn't matter. Now you could have spontaneously in some moment, all of a sudden they lined up in some order. In reality, something like molecules, this could actually happen. Probably more likely it doesn't, but it's probably more likely to have molecules line up like this than people. However, if you do work, and by work in this case, the drill sergeant comes in, he can force this to happen. And so it doesn't spontaneously happen, but it can be forced to happen. Right, and so there are ways natural processes tend to try to force disorder to go back to order. You know, things like taking food and things like that as ways of getting energy back. You know, you eat, you get more energy. That's one way to replenish your body and to have more energy than not having energy. And sleeping, you know, you get back energy. And these are natural ways, but they take work. And the biggest thing about this is it takes work to make a system be ordered, be quality. You know, cars, they break down, takes work to fix them. Houses, they break, takes work to fix them. People, our bodies, take work to get them up to standards. You know, even if you're dealing with climate change, it takes if you were putting pollution into the atmosphere, you know, it takes work to get that out. It takes work to counter what you're doing that's maybe negative. All right, so let me delete this so I can write. Go on to the next thing. Okay, so this brings in the idea of enthalpy. And this is amount of disorder, right, or the natural degrading of the system. And we label this with a delta S, okay, or the change in disorder, I should say. And if no work is put into the system, the amount of disorder is always going to increase. So delta S increases with no work being done. Okay, so the only way we decrease S is to put work into the system. So delta S itself is equal to Q over T. Now, we're going to see, let me make sure I have both types of problem in here. I do. I want you to remember there's two ways of calculating Q depending on if you're looking at a change in temperature or if you're looking at a specific temperature. Okay, so we're going to do problems kind of with both. Okay, so delta S is the change in enthalpy. T is going to be a constant temperature. Q is going to be heat added to the system. And for delta S equaling 0, this is for something that would be considered idealized and reversible process. Okay, so what does that mean? Well, best way for me to sum it up, and some of you may not get this reference, but I'm hoping that, you know, a lot of you do. If you ever played Minecraft and built mechanisms or farms. You have a couple types of farms. You have an automatic farm. I wish I could just pull up Minecraft and do it and show you guys, but it'd take forever. Or you have a semi-automatic farm. Okay. So what I mean by automatic farm? Well, I'm going to try to draw this. You can set where you have a block that grows a watermelon. And in the game, the watermelon and pretty much everything is square. So this grows a watermelon, and the block to the one side of it has to be a seed to that watermelon because it has to grow onto that spot. And then you need water. Also, somewhere, usually you can put water right to the side of it. And then dirt beneath it. Okay. And then what you can do is, and I have a better way of doing this actually, but I'm drawing it out, so it's a lot harder to draw exactly how I would do it, but for I'll say it in purpose, this would work. You have what's called a piston. And this piston operates on what's called redstone, and you can set it to a timer. Okay, I'm not going to really draw out the timer, but it sets it to a timer making a loop. And that piston starts always kind of pushing out and breaking whatever there. So if there's a watermelon there, then it breaks the watermelon goes into the water, and if you have the water kind of go and flow into what's called a dropper, and the dropper can throw into a chest, and then you can open the chest and get the watermelon out. Okay, this system is reversible, meaning once it breaks that watermelon, you still have the plant there. And the plant will eventually grow another watermelon, and it break that watermelon. And the plant will grow another watermelon, breaks that watermelon. You don't have to do a single thing. All you have to do is pick up the watermelons that flow into the river and into your chest, and you get all the little watermelons. That would be considered a fully automatic, reversible system. Basically, if the initial state is that you have a plant here and a spot for it to grow a watermelon, it always reverts back to that initial state, with the only exception being that watermelon grows or accumulates into your chest. That's a reversible system. A non-reversible system I'm trying to delete that picture. Would be if you have let's say sheep. I'm not going to draw a sheep, but if you have two sheeps and in the game you have it blocked off in like a pen. So I'm just going to use X's for the sheep here. So this is a pen around them, and there you have them trapped in something that doesn't allow them to move. But normally what I have is two sheep over here, two sheep over here, and this space is open. They're each trapped in usually a minecart, and you give them food. Give food. It causes them to breed. They drop a baby sheep, so a little X down here. And then you put something here that if they grow up into it, it kills them. And when it does, you get all these, you have droppers down here. And goes into a chest. Okay? And so the baby sheep grow up, and as soon as they do, they suffocate into this wall or something, and it kills them, and you get the food. This is semi-automatic. Why? You have to feed them. You have to feed them, and you have to feed them. You always have to go back. It never reverts back to a spot where you don't have to add fuel. And the food here would be considered fuel. Okay, this will be known as more of a real process, where the entropy of this always will increase to the point where you have to go back and fix the machine in a sense. Alright, so those are two Minecraft ways of doing systems. Right now, for the ideal one, your delta S is 0. For the real process, your delta S will always be greater than 0. And so what ends up happening for the real process is your delta S equals your delta S of the system plus your delta S of the environment. And that has to be greater than 0. So the total entropy of any system plus that of environment increases as a result of natural processes. All right, so let's get into a couple examples here. Give myself more space here. Let's say we have 1 kilogram of water at 35 degrees Celsius, which I'm going to change that to Kelvin right off the bat. So I'm going to add 273 and get 308 Kelvin. And that's that. I'll call it mass 1 for right now. 1 kilogram of water. And just so we have it, specific heat of water is 4,186 joules per kilogram Kelvin. Alright, so that's the first line. Not even the first line, first few words. We're mixing that with 1 kilogram of water, which is still 4186 joules per kilogram Kelvin, at 45 degrees, so that's 318 Kelvin. In a well-insulated container. We'll estimate the net change of entropy. Okay, so when we do this, because we have equal masses, because we have the equal system, we could go through and do the math, but the final temperature of both of these is going to be 313 Kelvin. Okay. I'm not going to go through that math. It will take a little while to do. It's not the important part of this. That would have been done in chapter 14. The important part is that we're doing entropy here. So we can look at the Q, the mass times the specific heat times, right? And we went from 313 minus 308. So we get 1 times 4,186 times 5. Right, which, let me pull out my calculator. 4186 a total 20,930. Alright, so what we now have to look at here is we have to look at a change in temperature for each one of these. Alright, so the change in temperature for T1 is going to be T1 minus what's T1? T1 is 308. I'm sorry. Hold on a second. Let me write out how I want it written. T1 average. Okay. It's going to be the average of T final minus T1 over 2. So 313 minus 3. Oh, I'm sorry, not minus, plus 308 over 2. Right, which becomes 310.5 Kelvin. Right, and then also T2 average is T final plus T2 over 2. So 313 plus 318 over 2 gives me 315.5 Kelvin. Right, and so we can say that the total delta S is going to be the 20,930 joules over 310.5 Kelvin minus 20,930 joules over the 315.5 Kelvin. To get, let me do the math here, divided by 310.5, get 67.41 minus 2930 divided by 315.5, 66.34. A little farther, 66.34. So we get 67.41. Oops, got the point or didn't come up. 0.41 minus 66.34 gives 1.07. And that's our delta S. Alright, so next problem. We have 50 grams of ice melts into water at 0 degrees Celsius. Okay. 0 degrees Celsius. Okay. We are using a formula that involves dividing by T. So we definitely have to convert this to Kelvin. So that's 273 Kelvin. And 50 grams of ice, so we need a line heat of fusion for ice, which is 333 kilojoules per kilograms. Again, this is in a table. And then the mass is 50 grams, which is equal to 0.05 kilograms. So delta S equals 0. I'll write this out. Q, which is mass times line heat of fusion over the temperature. So 0.05 times 273 over, I'm sorry, 273 is on the bottom, 333 . 0.05 times 333 divided by 273. And you get 0.061. Let's see, kilojoules. That's going to be here. Kilograms cancel out over Kelvin. Right, so we can multiply that by 1,000 if we wanted to. And we get 60.99 joules per Kelvin. All right. So there are some ways we can do things that can use this second law of thermodynamics. Some ways we use it as is. Other ways we use it opposite of the way it is. So, for example, heat engines, they produce work using thermal energy. So there is usually a hot source. So we can think of this as a car. Not going to draw a car this time. The hot source is the engine. There's a low source or a cold source, which is your exhaust. Okay, so we put heat in to get the engine working. That engine, some of the energy gets used as work and performs the operation. So work done is the car running. And some get wasted into low temperature and become exhaust. Right, so some of the heat in the heat engine, some of the heat is used for mechanical work, and some of the heat or some of the energy gets wasted into the exhaust. Okay, ideal heat engine cycles back to its original state. Cars do not. You have to continue to put energy back into this high temperature system. And we'll actually see that, unlike Minecraft, there really is no ideal heat engine. We will go through one where it's a theoretical ideal system, and that's a way to actually tell about the efficiencies of the system. So we're going to be getting that too. So in an ideal heat system, the energy will cycle back and you get no change in energy. So delta U will equal 0. That means that we can look at this in the quality of energy on your hot source equals the work plus quality energy in your low source. So in other words, this energy here either goes to work or goes to low temperature or goes to exhaust basically. Right. And so this is going to get into the third law of thermodynamics. Let me see where I'm at. 40. I will start that in the third and maybe the final video. I'll see. What page am I on? And maybe it would do in one video. Okay, I'll see you in the next video.